Hi everyone, let's find some domains. Again, we are looking for all real values of x for which the resulting output is real. Let f of x equal the square root of x minus 3. Find the domain of f, the implied domain of f. Well, when are we guaranteed a real output? When the radicand here, x minus 3, is what? What's that long word? When it's non-negative. It could be 0, it could be positive, it can be non-negative. So root x minus 3 is a real output if and only if the radicand x minus 3 is non-negative. It could be positive or 0. We can add 3 to both sides of this inequality, and we get x is at least 3. X is greater than or equal to 3, which is the key. Notice here, these are weak inequalities. The bars here indicate that 3 itself is legal. 0 itself is legal for the radicand, x minus 3. The square root of 0 is 0. Don't forget that. That's legal. That's real. So the domain of f in set builder form is the set of all x in the reals such that this over here, the key, x is greater than or equal to 3. You can use a colon instead of the slash. Here's the graph. We include 3 and get all greater numbers. In interval form, again, 3 itself is legal. We have the bracket there, bracket 3, comma, infinity, parenthesis. Typically, I'll ask for the interval form when I want the domain. Now that's the domain for f, where f of x equals root x minus 3. And it didn't matter if I used x or, for example, t. I could have said that the rule is given by f of t equals root t minus 3. And it wouldn't matter. The domain would still be the same set. I don't care if you put t's here, or x's here, or grandmas here, as long as you're consistent. It's the same set of numbers, all real numbers that are greater than or equal to 3. I don't care what letters you put here. Just be consistent. How would this domain be different? We just found the domain for root x minus 3. The domain for root x minus 3, the set of all real numbers greater than or equal to 3. How about f of x equals 1 over the square root of x minus 3? What happens is that radical is in the denominator. How would the domain be different? Well, when is this output real? The output is real if and only if the radicand x minus 3 is what kind of value? Here, x minus 3 must be strictly positive. We have a strict inequality here. The radicand cannot be 0 because root 0 is 0, and we cannot divide by 0. Add 3 to both sides, and we get x is greater than 3. So the domain of f is a set of all real numbers that are strictly greater than 3. 3 itself is illegal. Notice the open hollow endpoint over here at the 3. In interval form, instead of a bracket, we have an open parenthesis. 3, comma, infinity, parenthesis. So it makes all the difference in the world if the radical is in the numerator or in the denominator. How about this? Let f of x equal the fourth root of 3 minus x. Find the domain of f. The hard part is actually not the fourth root. We may as well be dealing with a sixth root or a square root. The bottom line is that we have an even root. This may as well have been a square root. The thing that's tricky is the fact that the radicand is 3 minus x, not x minus 3. So when is this output real? When is this output real? The output is real if and only if the radicand is non-negative, greater than or equal to 0. It can be 0 itself. Now, let's solve this inequality for x. And there are a couple of ways we can do this. This is a review of section 0.12 on inequalities. All right, method 1. We can subtract 3 from both sides. We get the opposite of x is greater than or equal to negative 3. And then we could multiply or divide both sides by negative 1. But remember that when you do that, what happens? The inequality symbol flips, and we get x is less than or equal to positive 3. We reverse the direction of the inequality symbol when we multiply or divide both sides by a negative number. Now, there's another way we could do this. Method 2, we could take 3 minus x is greater than or equal to 0. We could add x to both sides. Add x to the left, add x to the right. And then we get 3 is greater than or equal to x. And then we can switch sides. When we switch sides, again, we must reverse the direction of the inequality symbol. This time because we're switching sides about an inequality symbol. X is, again, less than or equal to 3. These inequalities lead to the same set. The domain of f is the set of all x's in the reals such that x is less than or equal to 3. The graph includes 3 as a solid endpoint, and we extend to the left. We want lesser numbers as well as the 3. The interval form follows the real number line going from left to right. The left arrowhead here sort of corresponds to negative infinity, and we always put a parenthesis next to negative infinity. Negative infinity, comma, 3, bracket. We do include the 3 itself. This is a trick question. F of x equals the cube root of x minus 3. Find the domain of f. For what values of x will this be real? Well, all real numbers. The domain of f is all real numbers. In general, if you're taking the odd root, like the cube root, the fifth root, the seventh root of a polynomial, if you're taking the odd root of a polynomial, the domain is all real numbers because we're taking the odd root of a polynomial. If f of x is the 11th root of a 20th degree polynomial, what's the implied domain? R, the set of all real numbers. Next up, all right, this is the big test. Find the domain of G. Next time.